Section 15.1, Absolute Value, Equations, and Inequalities. So the absolute value of a number represents the distance from that number to 0 on the number line. So when we're asked the question, what's the absolute value of 5, we think about how far away from 0 is 5 on the number line, and it's 5 units to the right, so the absolute value of 5 is 5. When we think about the question, what's the absolute value of -7, it's 7 units to the left of 0 on the number line, and when we do distance, we never report it as negative, so we would just say the 7 part of that distance, and say the absolute value of -7 is 7. Alright, moving on to another example. Let's look at part C, where they want us to solve the absolute value of x plus 3 minus 3 equals 2 minus the absolute value of x by using this graph. So the graph here, we have one graph, y equals x plus 3 minus 3. Notice that's the left side. And on the other graph is y equals 2 minus the absolute value of x, and notice that's the right side. So we've done this before on the graphing calculator where we graph the left side and the right side, and when we do that we always look for the points of intersection. So here's a point of intersection, and here's another one. So if the graphs intersect in two places, then we would expect that this equation has two solutions. And so we want to look at the ordered pairs to help us sort out what those solutions would be. This first intersection right here seems to be left 4 and down 2, so that intersection would be -4, -2. And this one is right 1, up 1, so that one is the ordered pair 1, 1. So which of those would we use? Well, if you look back up here, we're trying to solve for x. So we have two answers for x's that make the graphs intersect. One is x equals -4. And then the other one is right here where x is equal to 1. So remember that when you're using a graph to solve an equation and you've graphed the left side and the right side, it's the input variable that represents your solution. So there's our two answers and really not much work, just reading those off the graph. So let's look at a similar version of that where it's up to us to look at the graph and create the intersections, but it's a very similar problem. We have an absolute value on each side and they want us to use the intersect feature on the graphing calculator to find the answer. So I want to let y1 be the left side. There is no like straight up and down absolute value lines on the TI-84. What they have is a function that says ABS, which stands for absolute or absolute value, and instead of the lines after the ABS you put parentheses. So when I put ABS parentheses x plus 3, that would be read as the absolute value of x plus 3, and it would be just like this. So y1 I want to be the ABS of x plus 3, and then the plus 2 is outside the absolute value. And then my other graph would be the right hand side, and that would be 9 minus 2 times the absolute value of x plus 4, so that'll be ABS x plus 4. So we're going to want to graph those and then look for the intersections just like we did on this problem here. So let me go ahead and show you how to put that into the calculator. So we're going to go into the y equals menu, and our first function is going to be the absolute value of x plus 3. So we need to know how to find the absolute, and there's a couple buttons we have to press for that. The first one is the math key right here. So I press math, I go to the NUM for numerical, and the top one is the ABS. So math, numerical, ABS, and then I can put my x plus 3 and then the plus 2. And then you'll see all those steps again. We're going to do 9 minus 2 times, and then it's the absolute value of x plus 4. So I'm going to hit math, go over to numerical, and then absolute value is highlighted, so I press enter and enter in the x plus 4. And then I want to graph these and see where they intersect. Not sure exactly where that's going to happen, so I'm just going to go ahead and hit zoom and standard to get the -10 by 10, -10 by 10 window. So let's do that. So there's our first graph, there's the second, and just like on the one we had on the example above, there's two intersections. So we want to go ahead and find those. So remember that's in the calc menu, so I hit second and calc, and I want an intersection. And it's going to say, is y1 your first graph? Yes, by pressing enter. Is y2 your second graph? Yes, by pressing enter. And then it's going to ask for a guess, and this hasn't been very important up to this point, but now in order for us to get the right answer, we have to enter a guess that's close to the intersection we want. So if I have my flashing cursor near this left intersection, then when I press enter, that's the one it'll find. If I want to find this one, I'll need to move over there, and we'll see that in a second. So it looks like one of the intersections occurs at -6, 5. And we'll see where the other one is by doing that over again. So second calc, intersect. First graph is y1, yes. Second graph is y2, yes. But I don't want that guess, or I'll just get the same answer. So I'm going to arrow over and say, no, my guess is right around here. And when I press enter and it finds the intersection, it should lock in on that one. And so let's see, they didn't give us rounding directions here, so let's just round to a couple decimal places. This one would be approximately -1.33, comma 3.67. So if we were to solve this using the intersect feature, remember that it's the x that is our answer. So this is one of our answers, and that is the other one. So I would give the answers x equals -6, or we also have the answer x is approximately equal to -1.33, which is -4/3 if we wanted an exact answer. But typically on MyMathLab, if they're asking you to use intersect, they'll ask you to round. So let's go ahead and just add those rules just like they would on MyMathLab, and let's say let's round to 2 decimal places. And again, I kind of made that one up on the fly, but you'll always see rounding directions like that in MyMathLab. And then just a reminder on how we got the absolute value portion. We hit 2 keys to get there. We chose the math button, and then we went to the NUM for numerical menu, and under that we found ABS. Alright, continuing on with absolute value, but now we're going to start looking at solving inequalities with absolute values instead of equations. So they want us to solve and graph this one and write the answer in interval notation, and we have the absolute value of x is less than or equal to 2. So if I restate that as distance, it says the distance from x to 0 is less than or equal to 2 units away. So let me go ahead and think about that graphically. If I were to draw a number line and put the 0 on there, and then think, okay, if I went 2 units to the left and the right, where would I be? So 2 units to the right would put me at +2. 2 units to the left would put me at -2. And then what do I want for solutions? According to this, I want anything that's less than or equal to 2 units away. So the or equal says I would want these points, so I'm going to put solid circles for those. And then if I want the distance between x and 0 to be less than or equal to 2 units, I have to stay in between these two values. If I went on to the right, I'd be getting further away from 0. If I went to the left of -2, I'd be getting further away from 0. And this says I want the distance to stay small, so I want those two boundaries, -2 and 2, and all the points in between. So that's a graph of the solution. The way I would write the solution out would be to say that x is in between, using the less than or equal to symbols both times, -2 on the left side and +2 on the right side. And then the interval notation would be that x is an element of the interval that goes from -2 to 2. So just a reminder, this symbol right here reads as is an element of. And it's just a way of saying that x is in this range. So x is in the range from -2 to 2, or x is an element of the set -2 to 2. Alright, so let's look at a rule for that. Absolute value property for inequalities. For any expression a, so it could just be an x or it could be something more complicated, and any positive constant k, then if you have the inequality, the absolute value of some expression is less than or equal to a positive constant k, then your a will always end up in between -k and k. You might notice here they don't have the or equals. That's just because it didn't start with it. So if it starts with the or equal symbol, you'd keep it on. If it starts without it, you would leave it off. So let's go ahead and try that on a few more examples. So let's go ahead and solve and graph each of these, and we'll also write our answers in interval notation as well. So just like before, this property right here tells us what to do if we have absolute value of an expression by itself on one side and a constant on the other. When your absolute value has other pieces linked to it, the first thing you need to do is get the absolute value by itself. So I need to get rid of the 3 and the negative 1, and I would do that by first adding 1 to both sides to cancel those off. I get 3 times the absolute value of x is less than or equal to 12. 3 is connected to the absolute value of x by multiplication, so I would get rid of it by dividing. And that gets me to the absolute value of x is less than or equal to 4. Now that I have that absolute value by itself, I can try and get rid of it, and this shows me how to get rid of it. Notice there's an absolute value here, but when they say it's equivalent to this, the absolute value is gone. So it's always that negative positive two-case situation that allows us to rewrite the expression without the absolute value, in this case the inequality without the absolute value. So what we do is we put the x in the middle of two numbers. The number on the left is the negative one, and the number on the right is the positive one. And then I would solve for x if I needed to, but this x is already by itself, so that's my solution. Graphically, x is in between negative 4 and 4. We had the or equal to begin with, so we kept it all the way through, and that means we end up including those endpoints, so solid filled in circles. And then x is between, so we show a graph that connects in between. And interval notation, x is anywhere in that interval that goes from negative 4 to positive 4. And just remembering that when we have the or equal, we do the solid circles, but we also do the square bracket. Let's look at another one. Absolute value of 3x minus 4 is less than or equal to 25. This may seem similar to the previous one, and it is somewhat, in that it's an absolute value and a less than or equal to. But this time the absolute value is already by itself, but inside we have a more complicated expression. Well, if we slide this back down and look at the rule, this says whatever the expression is, as long as you have that absolute value by itself, you stick that expression in between the negative and positive of the constant on the other side. So if our expression has gotten more complicated, that's fine, but we're still going to trap that in between the negative and positive of the constant, so negative 25 and positive 25. And then because this was a more complicated expression, when we rewrite it this way we're not done. We still have to get x by itself, but we practiced these three-part inequalities before in previous chapters, so we're just going to return to that now and try and get this x by itself in the middle. So I would add 4 to get rid of that, and I have to do that to all three parts. So that cancels it in the middle, and on the left I end up with negative 21, and on the right 25 plus 4 is 29. Still focusing on the x, trying to get that by itself. I'd want to get rid of that 3. It's connected by multiplication, so I would divide all three parts by that 3, which would cancel in the middle. And then just simplifying, negative 21 over 3 is negative 7, is less than or equal to x. And on this side I can't reduce it, so I'll just leave that as a 29/3. And then when I go to graph it, we have a more complicated number, but when I do my graphs I just show the two boundaries, whatever they are, even if it's 29/3. The or equals are there, so I'm going to do solid circles again. And then x is in between, so my graph would go in between. And then finish it off by writing interval notation, so x is an element of the interval that goes from negative 7 to 29/3. And square brackets because of the solid circles, which came from the or equal being part of the original inequality. Alright, let's finish up with a few final examples. So again, we have an absolute value of an expression. This time there's some other stuff with it, the plus 8, and it's less than or equal to 5. So before we try and break this into two cases, we have to get the absolute value by itself. So I would do that by subtracting 8 from both sides. That cancels these 8s. And I get the absolute value of 5x plus 3 is less than or equal to negative 3. So if we were to look back at the rule says what to do if the absolute value is less than or equal to a positive constant, but it doesn't say what to do when it's a negative. And I'm going to argue what we do in that case is we just stop and think about it. When is the distance from something to 0 less than or equal to negative 3? Well, if the distance was less than or equal to negative 3, that would mean the distance was negative. And distance is never negative, so there's no solution to this. There's no x that would make the distance from this expression to 0 be less than a negative number. So when you have absolute value on one side, less than or equal to a negative, you always get the same answer, and the answer is that there's no solution. When you go to graph that, I guess if you were going to do anything, you'd just show a number line and draw nothing, because you would shade the part that is your solution, but there is no solution. And as far as interval notation goes, there's not really an interval to represent the empty set. You could show braces with nothing in it, which would be the empty set. You could use the symbol for the empty set, but there's not really an interval notation expression for that. So that's a special case. You just want to remember that if you're ever trying to solve an absolute value inequality and you get your absolute value by itself and on the other side you have the negative with the less than or equal or a less than, there's never a solution to that case. Alright, let's look at a couple more. The absolute value of 3x minus 5 is less than 10. This one has the absolute value already isolated. It's a positive on the other side. So we get rid of the absolute value by putting that in between negative 10 and 10. This is the first one we've had where the or equal wasn't there, so we don't put the or equal on these pieces either. And then we would go ahead and add 5 to get rid of the 5's in the middle, but whatever you do in the middle, you do on the outsides also. That gives negative 5 is less than 3x is less than 15. Still focusing on the center, trying to get that x by itself. The 3 is connected by multiplication, so we'd get rid of it through division. Division on all three parts. Doing that in the middle to get the x by itself. Doing it on the outsides just to keep everything balanced and equivalent. And then, what do we have? Negative 5/3 on the left, x in the middle, and 15 over 3 is just 5 on the right. So there was no or equal, so we left that off the whole way through. And when we get to draw our graph here, x is in between these two numbers, so we're going to put them on like we have on the other examples. But this time, because there's no or equals, we're going to do open circles rather than solid. But x is still in between, so we still draw the graph in between. And then remember, when your endpoints are not included and you go to interval notation, that you use rounded parentheses to indicate the endpoints are not included instead of using the squared off brackets. So there's my solution, my graph, and interval notation. Alright, let's take a look at one final example. And this one, I would actually argue, is just like the last one. Have the absolute value of an expression is less than or equal to, or less than, sorry, a positive constant. So just like that, except there's fractions. But the fractions don't really change what you would do. You would take whatever's inside the absolute value, 2x over 5 plus 3/2, and you would get rid of that absolute value by putting that expression in between the positive of the constant and the negative of the constant. And I've done this every time, but I haven't mentioned it. Your constants always have to have the negative on the left, positive on the right, with your inequality symbols pointing towards the negative or smaller one. So at this point, we've gotten rid of the absolute value. We just have an inequality that happens to have fractions in it. But the least common denominator of all those fractions is 20. So what we can do is multiply through by 20, which means multiply every term by 20. And we'd get negative 9/20 times 20 is less than 20 times 2x over 5 plus 20 times 3/2 is less than 20 times 9/20. And so temporarily that gets pretty messy looking. But when you come through and you multiply by all these 20s right here, the reason you're doing that is so you can cancel denominators, and it works perfectly. These 20s cancel. This 5 goes into that 20 4 times. This 2 goes into that 20 10 times, and these 20s cancel off. So let's see what's left over. All that's left over on the left is negative 9. Then going into the middle, we have 4 times 2x, which would be 8x, plus 10 times 3, which would be 30, and then just a 9 on the right. So by multiplying through by 20, we've gotten rid of all of our fractions. And now we can start trying to get the x by itself. So subtract 30 from all three parts. It'll cancel those off in the middle. That takes us to negative 39 is less than 8x is less than 9 minus 30 would be negative 21. And then we want to get that x finally by itself, so divide by 8 in the middle. Do that on the outsides also for balance. Your 8's cancel. You get x in the middle, which means essentially we've now solved this. We just want to write our solution. Negative 39/8 is the left boundary. Negative 21/8 is the right boundary. And messy fractions, but it really doesn't bother me because when I go to graph it, I'm just going to list the two numbers anyways. Negative 39/8 on the left, negative 21/8 on the right. These are less thans, not less than or equals, so the endpoints are not included, so I do round circles. X is in between, so I graph in between. And then just finish it off with interval notation. Our solution would be any x that is in the range from negative 39/8 to negative 21/8, not including those endpoints, and we indicate that with the rounded off parentheses. Alright, that finishes off section 15.1.